Let's talk about anisotropy. So we know that the universe is not homogeneous and isotropic at small scales, as we notice structures like cluster or voids in the local universe, for example, in the universe. And I want to introduce the context. So there are two notions, the preferred directions in the universe and also the cosmic web. So first, for the preferred directions, you can see here two projected maps of the entry points across the virial sphere. This is a lambda simulation. So this shows each point corresponds to entry points across the virial sphere at different values of the virial radius. You have 1 times RV and 3 times RV. And we notice that the points are clustered in a patch of the sky that is represented roughly by a green circle in both plots. And this suggests the existence of a preferred direction of accretion within the local group. And the second part is showing a slice of a density slice of a lambda simulation of the close collaboration. And I just want you to pay attention here to the green line for both M31 and the Milky Way. The green line corresponds to the direction of those circles in the sky maps. And we notice that they are pointing towards this white filamentary-like high density region. Then the cosmic web describes the anisotropic assembly of matter. It allows us to identify preferred direction in the universe. So this plot shows the peculiar velocity and related overdensity field reconstructed from the cosmic flows 2 data set by means of the Wiener filter methodology. And we are also showing the shear eigenframe by those 3 arrows, and they tell us about the shape of the filament that is connecting the local group to Virgo. So we see that it is compressed in the E1 direction by the local void, another compression in the E2 direction, and also stretching in the E3 direction induced by Virgo. So by using this definition of the cosmic web, we are going to answer the following question. Are the preferred direction of accretion in the local group coincident with the local cosmic web? So for this work, we use high-resolution simulations from the HESTIA simulation suite, which is a set of low and high-resolution simulations of the local group, so constrained. The cosmic flows 2 peculiar velocities and Wiener filter reconstructed velocity field has been used for the initial conditions. And in this work, we are going to consider all 3 high-resolution simulations. So first, we need to identify the accreted satellite galaxies. We define satellite galaxies as subhalos that are located within R200 of the main host, either Milky Way or M31, at redshift 0. And then we track them backward by looking at the merger tree. And the moment of accretion is defined when the subhalo crosses the inflow threshold that we define either at R200 or 2 times R200. We will see later. And this can be done by examining 2 adjacent snapshots. So a subhalo is accreted when in the latest snapshot it is inside the inflow threshold, and in the earlier snapshot it is outside. So by going backwards and following the trajectory of the satellite galaxies, we can identify the place and time of infall, and then define infall parameters such as redshift, the mass, and also, which is the main parameter we're going to look at, the direction of infall. And what we want to do is to compare the direction of infall to the cosmic web So for that, we will use the 3 eigenvectors of the tidal tensor, and we are going to look at the angle between the 3 eigenvectors and the inflow direction. So for simplicity, we are going to look at plots showing this distribution of the cosine of this angle. So if the distribution is peaking at 0, it means that the vectors are orthogonal. And then if it's peaking at 1, it means that the vectors are aligned in the same direction. So let's see. So first, we consider in the top plot the distribution of this angle at with an inflow threshold as R200. And so the 3 eigenvectors are colored in blue for E1, orange for E2, and green for E3. The gray regions here show the standard deviation, plus minus sigma for dark gray, and plus minus 2 sigma for light gray. And we also show the statistical significance over at the top of each plot, and colored by the same color code as the eigenvectors. So at this scale, R200, we don't see any kind of trend, which is mainly due to the nonlinear dynamics at this scale. But then if we shift the inflow threshold from R200 to 2 times R200, we notice that the green distribution corresponding to the angle with the E3 eigenvectors is peaking at 1, which shows a strong alignment of the inflow direction with the E3 eigenvector, which is due to the fact that from R200 to 2 times R200, we are shifting from the nonlinear regime to the quasi-linear regime. So now let's look for any dependency. So first, let's look at mass dependency. So the plot before this one is now divided into 3 bins of masses of satellite galaxies at time of infall. So from left to right, you have the lowest bins of masses to the larger bins, larger masses. And we can still see some trend with the green line corresponding to E3. And so the statistical significance is getting higher as we move toward larger infall masses. So we notice some kind of mild mass dependence because it is not that strong for larger infall masses. And before we look at the redshift dependency, let's look at the distribution of the redshift as infall. The M31 subhalos are in blue and Milky Way subhalos are in red. Then these 3 solid dotted and dashed line correspond to the 3 simulations. And then in bold, we combine all 3 simulations. So first, we notice that both Milky Way and M31 distributions are overlapping, which is quite nice. And we also observe 2 peaks, one at that we call late infall, after redshift of 0.7, and another one at early infall before a redshift of 0.7. And now back to the distribution of the cosine of the angle between the eigenvectors and the infall direction. So we have here 2 bins of redshift at time of infall. So one for the late infall and another one for early infall. And we see here a strong dependence as for the alignment with the E3 eigenvector, as the amplitude and the statistical significance is much stronger for early infall. So we see that the alignment with the E3 eigenvectors is dominated by early infall. And these are 2 height of projection of the virial sphere oriented in the tidal tensor eigenframe. So as the eigenvectors are non-directional, we only need to show a single octant of the whole sky map. And the direction of each eigenvectors are shown in blue for E1, orange for E2, and green for E3. And we show the Milky Way subhalos and the M31 subhalos separately. And also we are showing the direction to the simulated Virgo by those white scattered points in each plot. So the yellow pixel correspond to a high density of entry points, and the dark blue pixels show a low density of entry points, which we see that in both cases, we see a high density around the direction of E3. And we also notice some kind of difference between the Milky Way and the M31. The distribution here, the yellow region here looks more spherical for M31 than for the Milky Way. So let's have a closer and more quantitative look at this by looking again at the distribution of the angles between the eigenvectors and the info direction. I promise you it's the last plot I'm showing like this. So on the left, we show the Milky Way satellites only, and on the right, the M31 satellites only. And in both cases, we see an alignment with the E3 eigenvector. But in the case of M31, the statistical significance is stronger, 1.7 times higher, to be more specific. We may explain that the fact that the alignment is more stronger in the case of M31 by the fact that M31 is more massive as it is defined as such in the HESTIA simulations. So I am done with my talk, to be honest, and I'm going to take the rest of the time I have to present two other projects that are based on the Cosmic Phosphor catalogs. So Brent already introduced Cosmic Phosphor, so I don't have to do it. So this plot is showing, let's have a look at the left panel first. So this is showing the constructed overdensity and velocity field from the Cosmic Phosphor galaxies with a Hamiltonian Monte Carlo algorithm. And so in blue, you have the underdensities, in red, you have the overdensities, and then you also have the velocity field represented as black arrows. And you notice here, you can recognize some structures like Chaplet, Apus, Pachycetus, Coma, Norma. And you have also the SDSS part over there. And then one improvement of the Cosmic Phosphor construction is that we now provide the standard deviation on the velocity in the form of grid, which is shown on this panel. I forgot to mention this is a XY slice centered on z equals 0 in supergalactic Cartesian coordinates. So this is the standard deviation of the velocity field. In black, it's showing a low standard deviation, and then in yellow, a high standard deviation. And the white dot corresponds to the Cosmic Phosphor galaxies that I plotted over. And we notice that the error is the lowest where we have the data. And I just want to show you a three-dimensional visualization of the reconstructed field. So this is the same field as the previous plot. So we are showing here the overdensity field in the form of isosurface at 4 different levels. So in white, you have the lowest overdensity value, and then in dark red, the highest overdensity value. And then the peculiar velocity field is represented by streamlines. And we notice again all the known structures that we saw in the slice, as well as other structures that were not present in the XY slice. So we have Chaplet, Apus, Norma, Lepus behind, Hercules, versus Pisces, SDSS. So what can we do with the peculiar velocity field? We can look at the streamline in order to find attractors and identify the respective basins of repulsion, of attraction. So we have, through this method, this segmentation method, we have found several attractors, which are represented by the little red spheres, as well as the basins, which we are going to look at in more details here. So we have here 3 different basins, Laniakea, Perseus, and Hercules, which have been segmented, identified in the cosmic force flow velocity field. So you have here in blue, for Laniakea, the cosmic force 4 basin, and in yellow, the cosmic force 2 basin that have been identified a few years ago. And the shape is very similar. The new one is a little more thinner, I would say, maybe because we have more data to constrain the shape locally. And I don't have much time left, so I'm going to go around this second project very, very fast. So I'm also working on a new method to reconstruct the dark matter map from the observed peculiar velocity field with a deep learning methodology. So the training is done with the illustrious TNG 300 simulation, and we construct the training and validation sample like this. So we take the galaxy catalog we take subcubes inside the galaxy catalog to construct then the input layer, which contains the galaxy position and the radial peculiar velocity. And we also remove the zone of avoidance and apply a magnetic cut to mock observations. And then we also extract for the output layer a subcube at the same location in the dark matter density field of the TNG 300 to obtain the true value of the density field. And then we train the model with a CNN architecture. And this plot is comparing the true value of the dark matter density to the predicted dark matter density. So visually, they're very similar. The predicted dark matter density seems to be more less detailed, more smooth, but we still recognize the same structures. And we also see that we reconstruct overdensities within the zone of abundance region. And these two plots are showing more quantitative comparison, but I don't know if I have the time. I will just describe very fast. So the first one is a cell-by-cell comparison of the true dark matter density and the predicted dark matter density. And this is if they are matching perfectly. And the second one is a two-point correlation function. So in black, you have the true value of the density field, and in red, the predicted density field. So we see that even by looking more quantitatively, they're matching quite well. And lastly, here is the predicted density field. We apply if we apply our deep learning model to the cosmic force 4 galaxies. So you have here a XY slice centered on galactic coordinates. This is the zone of avoidance. In blue, you have the underdensities, and in red, the overdensities. So we can recognize the structures that we know. And this plot is showing sky maps in galactic coordinates. And we are overplotting in orange, yellow, orange, red, the cosmic force 4 galaxies. And in blue, this is what I want you to pay attention to. We are putting in blue galaxies taken from zone of avoidance surveys, these two surveys. And we notice here that the overdensities that are in black, light gray, black, are quite matching with the points. I don't know if you see them in the back, but they are matching with the blue points, the galaxy is an avoidance. So we are quite happy by the fact that we are constructing structures in the zone of avoidance despite removing the data within this zone for the training. And I leave you with my conclusion. Thank you.
Excellent. Any questions? And I'm going to run it. Okay. I was wondering, the late infall and early infall, were the masses the same, or I mean, do those two populations differ?
So
Yeah.
for the masses.
Oh, there. Oh, sorry, you did have the mass. Okay. So the
Yes.
mass matched. Okay, great. Thanks. Other questions?
So I'll ask a simple question. I didn't quite understand how you divided the late and early infalls. So you had this.
So yes, we observed in this plot that we have two populations of satellite galaxies. So most of the galaxies, the satellite galaxies, are being accreted very early in the accretion history of their main halo. And then we also observed another peak at after a register 0.7 of another population of galaxies being accreted much later than the other one.
And do you have any idea why?
Yeah, this is what we are wondering, to be honest, and we are thinking that it's because we are not taking into account backsplash galaxies, so we are not removing them from our studies. So they may be the cause of such of the fact that we are seeing two peaks. I think they noticed that in a study with the TNG simulations, and they also found that it may be due to backsplash galaxies.
Maybe I missed it, but can you say a word of when you reconstruct the dark matter map from the neural network?
Yes.
On up to what scale can you go?
Yes.
I mean,
yes, I went very fast at that point, so I missed many details. So for now, we are constructing the dark matter map within 40 megaparsec H. We decided to do this because we wanted to try to differentiate ourselves from the cosmic flows reconstructions, which are going very far, and the resolution is not that high. So we decided to reconstruct the density within cubes of 40 megaparsec H and 128 cube voxels.
so you're saying that the resolution of the reconstruction is about 40 divided by 100, yes. So something like
yes. So we are in the nonlinear scale.
So you are really in the nonlinear.
Yes.
And how reliable is the reconstruction in this nonlinear?
Well, I am not showing it here, but we can also do error maps on the density, and it's okay. And I mean, we can also see it when we compare it. There we are missing the small scale details, but we are still seeing somehow the same shapes, the same structures, and also when applying it to real data, it fits with the observed universe.
Okay, thank you.
Thanks. I have a question related to the previous one. So the fact that you have a map that is smoother than the ground truth. Yes. Yeah, exactly. So do you think it's because the information is not there in the inputs, or is it some fundamental limitation of your method, or is it due to the properties of the network or the technique that you used? So what is the limiting factor to recover the small scales?
I think it may be due to the architecture we are using, or maybe due to the loss function we are using. For now, we are taking this one, but maybe by changing the loss function, we can focus more on under densities or over densities, depending on what we want to study.
So you mean that you are quite confident that you can recover these scales actually just by changing the details of the method?
We are currently working on it.
Okay, thank you.
Other questions? Okay, so I'll ask again, very naive question. In your early part of your talk where you showed us Milky Way and Andromeda, and
For the height of map, or
so this is from these measurements are done on the data or on the simulations?
oh, no, this is done on the simulations. So
Right.
we are just differentiating the satellite galaxies that are being accreted within the Milky Way sphere on the M31 sphere.
Yeah. So I always thought that it was super difficult to construct simulations where you reproduce the Milky Way and Andromeda in them. And so how much are we supposed to, is there wiggle room for those positions? And you know, can you discuss that a little?
The HESTIA simulations are constrained with the Cosmic Force 2 dataset, so they are supposed to look like our universe. And at least this is the case for the three high resolution simulation. We have the Milky Way and the Virgo in all cases, but then we also have, I think, a little less than 20 low resolution simulation, and I don't think they are. We have local groups looking perfectly like it should. So, but most of them are still okay. I did a test as well on the low resolution simulation, and most of them give the same result.
Okay, thank you. So can the next speaker put up their talk? And is there any final question? Here's a final question. Excellent.
I guess it's kind of related to the fact that this is supposed to be done on, so HESTIA is a constrained simulation of the local universe. And when you showed that, you know, the position, the direction of infall for both Milky Way and M31, I would have, and you said you would have folded it into one octant, but that's a little bit, that seems like you're throwing away a little bit of information, because in principle, for example, there should be a filament connecting to Virgo, and, you know, like basically, you know, there's probably, you know, the local voids on either side. So I felt like if you do like a Mercator projection around the galaxies, the infall directions should be pretty obvious. Yeah, did you check that?
No, I have not checked that, but this may be part of a future study. Thank you.
Okay, so perhaps we should thank Alexandra.